morning everyone. Welcome to yet another week of the course in NPTEL MOOCs titled Artificial Intelligence in Industrial and Management Engineering. I am Professor Deepa Philip. I am from IIT Kanpur, and this course is offered as part of the NPTEL MOOCs content from IIT Kanpur. And along with me, Dr. Prabal Pratap Singh is co-teaching this course. Once the initial components of it is what I covered, then Dr. Prabal will come forward and then he will take the application side of it on how to develop these using various computer program applications, etc., and work out few examples, real-time examples, so that you have a skill development also as part of this course. So we have seen many topics as part of this course so far. We have seen what is industrial engineering, why industrial systems are critical, why the management decisions associated with operations decisions associated with industry is important. And we also seen how some of the decisions can be made with the help of a computer, and what is AI, and some of the simplest ways in which AI can add value in industrial and management engineering. That's what we have been looking so far. And we have seen knowledge and knowledge representation and how knowledge can be used to make decisions. And we are slowly transitioning into the topic called expert systems. But today we are going to now continue with some of the things that we covered last week, specifically on how we studied forward and backward chaining. And if you look at today's slide, what we are going to do is we are going to work a small example of backward chaining. And this would help you quick example will help you to understand that. So backward, you remember that the key word is existing knowledge in this, right? We have like capture existing knowledge. This was our key aspect in this. That is something that is part of all knowledge based systems there. So let's take, for example, let's take a small known data set that we know. Okay, we'll just store this as a table for the time being. Okay, we'll say name, then we'll say relation, quantifier / value. Okay, so let's think about this in a tabular form. It is typically represented in other ways, but this is done in a tabular form. Let's take name as Mustang. The relation is a, and the quantifier is a horse. Okay, we have, let's say, multiple rows. So then Blackie is a horse. Okay. Then we say Blackie is a parent of Dasher. Okay, we are doing horse racing today. Okay, and Blackie is a parent of Mustang. Okay, then we also say Mustang is fast. It's a fast horse. Okay, now I'm just doing it in the tabular form so that it's easy for you guys to understand. Then we say Dasher is a parent of Fasty. My horse names are horrible. You have to understand that. Fasty is fast. Okay. Then we also say Fasty is a horse. And we also say Dasher is a horse. So if you look into this table, you can see that you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, what you can call it as a knowledge, facts, information that is being stored in the form of a table. Okay, it's somehow captured in the system. So with that, now let's see what is the rule. Okay, and you remember there is knowledge and then there is rule. Okay, so the rule is if. Remember we talked about if else, if then. Okay, if. Okay, the first part is X is a horse. The variable X is a horse. Then second is variable X is a parent of variable Y. Okay. Then third one is variable Y is fast. If these three conditions, if variable X is a horse and variable X is a parent of variable Y and variable Y is fast, then we say that variable X is valuable. Okay. So if you look into this, you can see that some of them there is an is a horse relationship, there is a is a parent relationship and there is a fast relationship. We are trying to use the three to decide whether the variable X, if it is a horse, which is valuable. So that is the simplest way. So this is a, we can think about it as a rule that can result in an inference or conclusion. Okay. So how do we, what is the first thing to do? So we say after defining the rule, what is the next step? So what is the next step as part of this? So the next step is find bindings. So find bindings means find relevant information / data from the available knowledge or available knowledge, or what you can call it as existing knowledge. Okay. So what are some of the, first thing is if variable X is a horse. Okay. So then variable X can be bound to, okay, variable X can be bound to, we go back and see which are the horses. So in this case we can say Mustang is a horse. So the horse relationship is here. Blackie is a horse. So that's another horse. Then you look through this one, you see there's a horse. So Fasty is a horse. Okay. And Dasher is a horse. So you have, from the existing knowledge, you are 4 horses: Mustang, Blackie, Fasty and Dasher. So that are the bindings, bound to Mustang, Blackie, then we have is Fasty, Dasher. Okay. These are the 4 horses. Then similarly, next one is variable X is a parent of variable Y. So how do we look at the variable X who is the parent of variable Y? So we go back to this one. There is 1, 2, 3 is a parent of. So there is Blackie, Blackie Dasher, then Blackie Mustang, and then Dasher Fasty. Okay. These are the 3 ones. So then the parent of Y, so then we write it as Blackie Dasher here, then Blackie, Mustang, and then Dasher, Fasty. Okay. So, that is the second binding. Then the third binding is variable y. If you look at the rule before, you can see that variable y is fast. This is the third part of the rule. So, we go to variable y is fast. Okay. So, how do we find the bindings? We go back to the data and we look at who are the fast horses. So, Mustang is fast, Fasty is fast. Those are the only two fast ones. Okay. Mustang and Fasty. So, we go back and we say Mustang, Fasty. Okay. So, with these bindings that we are getting from the data, we have to come to what we call as the backward chaining, execute the backward chaining. So, how will you write the backward chaining code? Okay. What is the, so we will write the pseudo code for you, right, or I will call it as approach for the time being. Okay. So, I will say until all hypotheses have been tried and none have been supported. Okay. First thing is until all hypotheses have been tried and none have been supported, or in this case until the animal has been identified. Okay. This statement is more just for this problem, okay, only for this example. So, our aim is to identify the horse. Then until all hypotheses have been tried and none have been supported, or in this case until the animal has been identified, you have a loop for each hypothesis, individual hypothesis. Then you have underneath that nesting, okay, it will be nested underneath for each rule whose consequent matches the current hypothesis. Okay. So, for each rule whose consequent matches the current hypothesis, what do you do? The next one is try to support each of the rules antecedents by matching. You have seen what is an antecedent and consequence in the previous presentations, matching it to assertions in existing knowledge. Okay. Try to support each of the rules antecedents by matching it to the assertions of existing knowledge, or by backward chaining through another rule create new hypothesis. So, based on backward chaining. So, what is saying that try to support each rule's antecedents by matching it to assertions of existing knowledge. You either match to the assertions in existing knowledge, or by backward chaining through another rule create a new hypothesis. Okay. Then next step is ensure to check all matching and instantiating alternatives. instantiating alternatives. Okay. Then finally, we say that if all the rules antecedents, okay, the conditions, requirements are supported, antecedents, that is in if is supported, announce success and conclude that the hypothesis is true. Okay. If all the rules antecedents are supported, if all of those antecedents, so in this case, what are the antecedents that can need to be supported? All these are to be supported. Okay. If that is possible, then we conclude and declare that the hypothesis is true. Okay. So, that probably helps you to understand the logic. So, in this example, what we are trying to do is, until the animal is identified, for this example, we go through for each rule that we take whose consequent matches the current hypothesis. We support the rules, each of the rules antecedents by matching it to the assertions in the existing knowledge, or by backward chaining we try to create a new hypothesis. If we can't match, then we create a new hypothesis, and then we ensure to check all matching and instantiating alternatives, and if all the rules antecedents are supported, we announce success and conclude that the hypothesis is true. Okay. We do not need a question mark. So, let us do an example, working example. The working example is, then the thing is, start matching hypothesis against. To start matching the hypothesis against, first is existing assertions, second one is rule consequences. Okay. So, how do we do that? The question is, Blackie is valuable. This is our question hypothesis. Okay. The question is, Blackie is valuable. So, if you look into this rule earlier, we said that if X is a horse, X is a parent and Y is fast, then X is valuable. So, if we go through that and we write it down here again, rule is, if variable X is a horse, X is a parent of Y, Y is fast, then X is valuable. Okay. So, the question is, Blackie is variable. So, we can say X is valuable implies Blackie is valuable. So, X Blackie. Okay. So, now the question is, the hypothesis is Blackie is valuable. So, the algorithm says for each rules whose consequent matches the current hypothesis, you go through the antecedents. Okay. So, the valuables is that you have in the database, if you look into it, you have this entire thing from the database we need to match. So, now we start with what we call as Blackie. Okay. So, with Blackie, how does the backward chaining work? So, the next thing is, if Blackie is a horse, is this true? Okay. So, what do? We go back and Blackie is a horse. Okay. So, the assertion is matched. Yes, matched. The next one is Blackie is a parent of. So, now we go back to the data. Blackie is a parent of Dasher and Mustang. Okay. So, we have Dasher, Mustang. Okay. So, that means you have two cases to now look into. So, now we go separately. So, I will give you an example. Then the third one is, the third part of the rule that we have to look into is, it says variable y is fast. So, you have two things to check, which is Dasher is fast, Mustang is fast. Okay. So, with this premises, let us look at how this thing will work. Okay. So, the one way to represent is, or do it in such a way, is that we start at Blackie, variable is Blackie here, Blackie. Okay. Then under this Blackie, okay, we have, I would say, I am just drawing this to make your life easy, is a horse. Yes. Then we have parent of, then child fast. Okay. Is the child is fast. So, Blackie, this is a horse. Okay. Parent of, and in this case you have two options. Okay. Those are, in this case we have seen Dasher and Mustang. Dasher, Mustang. Okay. And now the other thing is, the child is fast. Okay. The question is, we have Dasher is Dasher fast, is Mustang fast. Okay. So, the question is this. So, we go back to the table and we find that Mustang is fast, and there is nothing that written Dasher is fast. Okay. Mustang is fast, that is there. Okay. So, we know that Mustang, we say, is fast. Okay. It is not. So, Mustang is fast, but then Dasher there is, okay, this is not known. So, what do you do now? Now, if it is not known, so then you can work from the Dasher side. Then you can say is that I am now using another color, is a Dasher is a horse. Yes. Okay, or I will just write it here, not known. We do not know whether Dasher is fast or not. Okay. We now look into what we call as parent of, and we say child fast. I am just writing it in such a way that you can kind of visualize how this will expand into. So, now if you think about Dasher, okay, we go back to the data. Okay, Dasher is a parent of Fasty. Okay. So, Dasher is a horse and Dasher is only the parent of Fasty. Okay. So, we have one here, the parent of, we have Fasty. Okay. And question is Fasty is Fasty fast. Okay. So, if you look into it, okay, we can see that it is defined that fast T is fast, okay, it is given. So, we know is fast, okay, and there is no other option to go below. Okay. So, you can see that there is two children actually, okay, fast T and Mustang. Okay. This is fast T and Mustang, two of them, which are, one is the child of Blackie, another is the grandchild of Blackie, both are fast. So, since Mustang is fast, okay, whose parent is Blackie, okay, can say Blackie is valuable. Okay. Also, the fast T, which is the child of Dasher, which is the child of Blackie, okay, is fast. Okay. That way also Blackie is valuable. Okay. So, if you look into this, this is how the chain or this example works out. So, we started with Blackie. This is, you can say, hypothesis 1, the first hypothesis, and the first question what we had, the is a horse is a parent of is fast, okay, the 3 antecedents, okay, 1, 2, 3, as we said. Then these 3 antecedents we go through, and from there we got assertions. Okay. So, the assertions came from Dasher, Mustang, and we know that Mustang is fast. So, here itself, okay, you can conclude here itself. This is also fine, okay, there is nothing wrong in it. But we also say, ensure to check all matching and instantiating alternatives. Okay. We need to look into that. So, one thing that is hypothesis 2 here, because there is something we do not know about Dasher. So, we need to look little bit more into, okay. So, this will complete. Okay. So, the conclusion below, because fast is also fast, which is a child of Dasher, and Mustang is also fast, which is a child of Blackie, Blackie is, so you declare. So, basically you can say that conclude, what are you concluding? Blackie is valuable. That is your conclusion. Okay. So, with this we conclude this small example that we have worked out so far, and I am hoping that you will look at similar examples and understand. So, this is a small toy problem, but it actually tells you how the backward chaining works out. And now we will slowly start moving into what we call as logic and expert systems, which is part of the next course content, and we will proceed accordingly. Thank you for your patient hearing. I will see you soon with the next lecture. Thank you.